Okay, wanted to do something a little bit different today, and we're looking here at an integral in a general form. We've got here the integral from 0 to pi over 2 of sine to the n of x over sine to the n of x plus cos n of x dx. And the reason I wanted to go over this is it comes up a lot in contest problems like the MIT integration bee or the UNSW integration bee. And what I want to show with this is that this integral is equal to pi over 4, and then in the process of doing that, we'll also see that this integral is actually equal to this and also equal to pi over 4. So let's just see how this is going to work. I'm going to start with our integral here, and we're going to make a u substitution. I'm going to make my u substitution based on these bounds, adding it together. I'm going to say u, we'll substitute with pi over 2 minus x, and so then x is pi over 2 minus u, and therefore dx is minus du. Then we'll just go ahead with this, and what's going to happen is our upper bound, we plug in pi over 2 becomes 0. The lower bound becomes pi over 2. Then just substituting in, we have our x value here, so we're going to end up with sine of pi over 2 minus u. And we're going to have the exact same thing over here. And then our cosine term is going to be similar like this. Now from here, what we can do is just use this minus sign to flip the bounds. So we're going to put that back. So the minus will change the bounds back, so it's going from 0 to pi over 2. But the nice thing here with all of these terms is I can use the complementary angle formula on this. So all the complementary angle formula does when you have this input of pi over 2 minus u, it flips the sines to cosines, the cosines to sines. So for example, when I do this, our sine of pi over 2 minus u is going to become just cosine of u. And then we have the same thing here. And this cosine is actually going to become a sine of u. And these are all to the n. Now at this point, I'm going to just do a variable change because it's a definite integral, so the variable doesn't matter. So I'm going to change this back to x and rewrite this. And now at this point, I just want to notice that what we have right here, this is exactly what we have right here. So we've shown this first part actually, that this integral is equal to this integral. And of course, if we started with this one instead of this one, at this point we'd just be back to sine because the complementary angle formula would flip the cosine in the numerator to a sine. But now what I'm going to do is I'm just going to label this I. And so if I do that, both these are I, so I can just add these two together. So when we add them together, we're going to have two copies of the integral, or 2i. And now we see that when we add the numerators together, we have exactly the same thing as the denominator here. So this is actually going to cancel and just be 1. And this is why in the original problem, we're just using n, because the exponent really doesn't matter. We could have chose anything on the exponent. N can be just about anything, and this is still going to cancel down to 1. So when we integrate that, we're just integrating 1. And so we're just going to be left with x from 0 to pi over 2. But evaluating this is going to give me just pi over 2. But again, this is two copies of the integral, so I need to divide by 2 on both sides. And so the solution of this, dividing pi over 2 by 2, is going to be just pi over 4. And that's what we're looking to prove. So I know I've done this a million different ways, but I don't think I've ever shown the general case like this. So we'll stop it there. Thanks everyone for watching. Have a great day.